Alrighty, lads and ladies, we are back. Today we're going to continue talking where we left off last time about rational functions. We're going to do one more problem where we practice the same sort of stuff we were doing last week, but then we're going to move into some slightly more complicated rational functions. Namely, we're going to deal with that little asterisk that we had behind our vertical asymptote rule last time. So without further ado, let's do the thing. All right, this is MAC1140, section number 009, which is a pre-calc class. And today is the 19th of October, 2021. Today we're going to do more rational functions. Which was 3.6. We're going to introduce polynomial and rational inequalities. Which is 3.7. And I also want to announce the solid date for exam 2. It's next Tuesday. I think we said this last week, but just to be clear, so early last week, last Tuesday, we said that the exam would either be this Thursday or the following Tuesday, depending on how much time we wanted to spend on rational functions. And then, excuse me, and then last Thursday, when we realized we're going to need a little bit more time to get through section 3.6, and then spend an appropriate amount of time on 3.7, that we would not be able to get to the exam by this week. So next Tuesday, which is the 26th. And the rules are the same as for the first exam, right? So if you're going to take the test here with me online, you'll need to use Zoom on your phone and HonorLock on your computer. And once you finish the test, you will need to scan using an app on your phone the written work, and then upload that to the assignment in Canvas titled Exam 2 Written Work. If you're going to take the test at the testing center, I will, you don't need to email me individually this time. I will make a walk-in reservation for you all. So anybody who wants to take the test at the testing center can do that, the big open lab in building N, and they will collect your written work after you finish the test there, and then I will pick it up from them. That is it. So the rules are the same as the first test. Of course, the material is what we've been talking about. I think I gave you a list last week. That'll be all the stuff that we've covered since the first test. So it's, quadratic functions, polynomials, their graphs, local behavior, end behavior, factoring, complex numbers, complex roots, fundamental theorem of algebra, and then everything we've done with rational functions. That's it. Format's the same as last time. It's going to be on Canvas. Same number of questions, same distribution between true, false, multiple choice, and free response. So everything pretty much the same as exam 1, just the content is different, right? It'll be the exam 2 content instead. What other stuff? I released a new homework for you today. It's already up. It's 3.6 part 2 and 3.7 part 1. Before the test, there will be one more homework and one more quiz, and I'll release those for you on Thursday. Okay. That's everything, I think. So let's get into it. I want to begin, like I said, just with a little bit more practice on the stuff we were doing last time. So this first example is not going to be anything crazy or new. I just want to kind of get your memories running. If you could, please grab out the page of your notes where I gave you that 5-step process for finding the graph of a rational function, because we're going to begin by sketching the graph of the rational function r of x equals 5x plus 21 over x squared plus 10x plus 25. All righty. So who can tell me what my very first step should be? I want to sketch this graph. Where do I begin?
Factor the top and bottom.
Very good. So our first step is always to factor top and bottom. The top here is a linear function. So there's really not much I could do. I could factor out a 5 if we wanted, but it's not going to be pretty because 21 isn't divisible by 5. So I'll leave the top alone. The top is good. But the bottom can be factored. How does the bottom factor?
X plus 5 squared, like the parentheses.
Good. It's x plus 5 times x plus 5, which is quantity x plus 5 all squared. Okay, so we've factored the top and the bottom. What do we do then?
We find the vertical asymptote.
Yeah, we're going to go hunting for asymptotes. So does this function have any vertical asymptotes? If so, what are they?
Is vertical asymptote the difference between powers of the top and the bottom?
That sounds more like horizontal asymptotes. So remember, vertical asymptotes, these are places where the function blows up to infinity, which means those are places where the bottom is 0. So the bottom of this function is equal to 0. This is why we factored at the start when x is equal to -5. So that's our vertical asymptote. And remember, when we find x-intercepts and vertical asymptotes, we want to note the multiplicity. What is the multiplicity of the factor downstairs that gives me that vertical asymptote?
2.
Yeah, it's 2, right? Because this is x plus 5 all squared. Very, very good. Okay. Multiplicity here is 2. That's going to be important. We also need the horizontal asymptote. And that's the thing that comes from this 3-case rule, right? So that has to do with the degree of the top and the degree of the bottom. Which one of those 3 cases am I in here?
The bottom is bigger than the top.
Yeah, the degree of the top here is 1. The degree of the bottom here is 2. So the degree of the top is less than the degree of the bottom. So since the degree of the top is less than the degree of the bottom, the horizontal asymptote is what?
0.
Very good. It's the line y equals 0. Okay, I've got my factored form, my VAs, my HA. What else do I need?
Find the intercepts.
Good. Yeah, we need intercepts. So there are x-intercepts and y-intercept. What is the x-intercept here? How do we find it?
You replace every x value with 0.
That's the y-intercept. So to find the y-intercept, we plug x equals 0. So let's go ahead and write that down. If I plug 0 in, I think it's easier to see from this form. You'll have 0 plus 21, and then downstairs, these are both 0 plus 25. So plugging in x equals 0, we find that r of 0 is 21 over 25. And you can put this in your calculator. This is like 0.8. But the x-intercepts, how do we find those?
5x plus 21 equal to 0.
I'm sorry, say that one more time.
The top has to be 0.
Very good. Yeah, the x-intercepts are places where the whole function is equal to 0. And that will happen if the top is equal to 0, right? Fraction is 0 if its top is 0. So we set the top equal to 0. Here that means 5x plus 21 is equal to 0. And that means that x would have to be negative 21 over 5, negative 21 over 5. And this is a little bit bigger than 4, right? This would be like negative 4.2. So I've got my intercepts now. There's one more thing I want to make note of here in the intercepts, kind of similar to this. I need to remember the multiplicity of the x-intercept. So what is the multiplicity here?
Isn't it 1?
Yeah, yep. This factor upstairs, 5x plus 21, is a multiplicity 1 factor. We could write that if we wanted as 5 times parentheses x plus 21 fifths, right? So that is a multiplicity 1 factor. Okay. Now that I have all of my asymptotes and intercepts, and I know the multiplicity of the VA and the multiplicity of the x-intercept, I am ready to start drawing my graph. And you'll see it's kind of like magic. From those multiplicities and the y-intercept, I will be able to get the whole damn thing. I think it's pretty cool. So my horizontal asymptote is this line y equals 0. My vertical asymptote, so here 1, 2, 3, 4, oh, I'm gonna go a little further. Negative 5. So we draw these in and we label them. I can also put my x and y intercepts here. So my x-intercept is negative 4.2, which would be like right there. My y-intercept, I haven't marked a scale here, I'm gonna call this 1, 2. So my y-intercept is like positive positive 0.8, which is like right here. And believe it or not, this is enough to do the whole thing. Here's how we do it. I want to fill in the local behavior near this VA, right? The arrows either pointing up or down on either side. I want to fill in the local behavior near this x-intercept, meaning like a cross or a bounce, either from below to above or above to below or below to below or above to above. And then that will allow me to fill in the behavior near the horizontal asymptote. Then once I have all that stuff, I'll connect it with nice smooth curves. The x-intercept is multiplicity 1, which is an odd multiplicity. So we're going to be crossing the x-axis, not bouncing off of it. There's two ways I could cross this x-axis, either like this, going from below to above, or like this, going from above to below. The trick to figuring out which of those to do, like this or like this, is to think about this y-intercept over here. There are no other vertical asymptotes or x-intercepts anywhere in this region. So if my function comes out here positive, it's going to stay positive until it gets over here. And if my function comes out of here negative, it has to stay negative until it reaches something. Because this is positive, I know I have to come out of here positive. Right? I have to arrive at this y-intercept positive. So I can't possibly leave here negative, because the only way to go from negative back to positive would be as if I had another x-intercept where I could cross. But I don't have another x-intercept, so I've got to come out of here positive. And because this is an odd multiplicity, I have to cross. So I'm going to cross from below to above like that, because I have to arrive at this guy positive. Does everybody understand that? a little sneaky. So we kind of use this as like our base point. This is the bit of information that's going to allow us to fill everything in. Positive here, no sign changes in here, means we have to arrive here positive. Means, and then because this is odd multiplicity, that means we're going to cross. So we're going to poke out down here negative. So how am I going to approach this VA on the right? Is my arrow going to go up here or is it going to go down here, and why?
Down.
Down, good. This arrow has to point down because I came out of here negative and there's no way I can change sign in there. There are no x-intercepts or VAs in between there for me to change sign. So because we poke out of here going down, we got to go down here. All right, what about on the left side of the VA? Is that arrow going to point up or is that arrow going to point down, and why?
Up.
So think about the multiplicity of the factor that gave us that vertical asymptote. That vertical asymptote came from a multiplicity 2 factor, right? So this factor doesn't change sign when you hop over -5. If you're negative on one side, you're going to be negative on the other. And if you're positive on one side, you'd be positive on the other. So because this vertical asymptote comes from a multiplicity 2 factor, the arrows have to point the same way on both sides. I know that the arrow has to go down on the right, therefore the arrow must go down on the left also. And the rule there, remind you, how do we want to say this? The function will not change sign as we pass over a VA of even multiplicity. That's the one that we're using here. And the kind of corresponding rule is that the function will change sign as we pass over a VA of odd multiplicity. So this is the rule for sign changes over vertical asymptotes. If the VA comes from an even multiplicity factor, the arrows have to point the same way on both sides, either down and down or up and up. If the VA comes from an odd multiplicity factor, the arrows have to point opposite signs, down and up or down and up. Since this guy is an even multiplicity, and we know the arrow goes down on the right, the arrow must also go down on the left. The idea is that that VA comes from this factor. And even multiplicity factors don't change sign when you cross over their roots. So this factor itself, if it's negative to the left of -5, it will be negative, this factor itself won't change sign. So if the function is negative to the left of -5, it will also be negative to the right of -5. That factor doesn't change sign, so the function doesn't change sign. All right, we're almost done. Since this arrow points down, just to the left of this vertical asymptote, do I approach my horizontal asymptote from above or from below? In other words, does the arrow over here,
From above.
we could come in from above like this or from below like this? Now remember, in order to go from being negative down here to approaching this from above, I would have to cross the x-axis, right? But I don't have any other x-intercepts. So because I'm negative down here and there's nowhere for me to change sign, I have to stay negative out here as I approach this horizontal asymptote. Remember this, it happens to be the case that my horizontal asymptote here is the x-axis. So if I wanted to approach this from above, I would have to have crossed the x-axis again and then start sneaking up on that asymptote. But there's nowhere for me to cross the x-axis over here. There are no x-intercepts. There's only one x-intercept, and we've already plotted it. So that means because I'm negative here, I've got to be approaching this from below. I've got to be negative over here also. And that means I can connect these pieces like this. Similarly, I can start stitching these guys together. I know that has to do something like that. It has to get over to that intercept here. You've got to go from here to here, and then from here to here. And now that means I'm going to be poking through my y-axis like this. My function is positive. And again, there's no x-intercepts or VAs over here. There's nowhere for me to change sign over here, which means on the right side, I have to approach that horizontal asymptote from above. So here's what my graph looks like. Something like this. And that's fairly complicated, but we were able to get it just from these things. The trick is to remember to record the multiplicity for your vertical asymptotes and your x-intercepts. Once you have all of that stuff, as long as you know the sign of the function, positive or negative, at one point, you can fill everything else in. Fun fact, the area of mathematics where I worked, additive number theory, we answer questions about whole numbers by kind of translating them into questions about functions like these. And functions like these in a slightly more grown-up math class are called holomorphic functions. Holomorphic functions are like glass. Once you have just a little bit of information about them, the entire function is fixed and rigid. So here, once we know the vertical asymptote and its multiplicity, the x-intercept and its multiplicity, and one other bit of information, in this case, we used the y-intercept, all of this behavior is fixed. Okay, just to be clear, this is something you are going to have to do on a test, right? So let me show you what a perfect 10 out of 10 would look like here. I would want to see these intercepts labeled clearly. This is the point 0, 21/25. This is the point negative 21/5, 0. And now you got it. Now that's a 10 out of 10. And you will have to do this on a test, right? On exam 2. There will, I promise you, there will be a problem where I just give you a rational function. I say, find all this stuff and then draw me the graph.
Professor, why isn't it like a straight line from the point -21/5 to the 1?
Yeah,
Like, why isn't it?
Interesting question. You could, so if you were to have connected this to this without a little hill there, I would have given you full credit. It turns out that there is a local maximum in here. That's a little bit hard to spot. And I wouldn't necessarily expect you to notice that. In my case, it was just a feature because I ended up drawing this little line like taller than this point. I had to turn around. So kind of on accident, I discovered that, but I think it is correct. The way you would figure that out down the road would be using some calculus. But here, it does turn out to be the case that there is a little hill here. There isn't anything in this procedure that tells us that. So just to be clear, if you were to miss this, if you were to just connect this like as straight as you could, I wouldn't take off any points because there isn't anything that we have available to us at this level that would help us find this max. But it does exist. It is indeed there. So it's a good question. And I've taught this class now. I'm teaching like 4 sections of pre-calc, and you are the first person to ask that. So congratulations for noticing the little thing I swept under the rug. Pretty much nobody has even acknowledged that. But yeah, it's not something that I would expect you guys to be able to find at this point. It's coming from the fact that something called the first derivative of this function happens to be 0 at like 3 point something, -3, you know, right around -3, -3.4, whatever this is. Yeah, -3.4. But again, it's not something I'd expect you to find. If you just connected this piece to this piece without any hill in between, still 10 out of 10. Wonderful question. Any other questions on where this graph is coming from? Okay, just looking forwards, if I asked you, where is this function positive, what would you say?
-4.2 to the infinity.
Excellent. Yeah, from here to infinity, right? And if we asked, where is this function negative, we would say from -4.2 to -5, and from -infinity to -5, these 2 intervals. So you can see solving the inequality r of x is greater than 0 or r of x is less than 0 is really all about 2 features: the vertical asymptotes and the x-intercepts. Those are the only places where a rational function can go from negative to positive or from positive to negative. So the next section where we'll be solving inequalities like that, instead of drawing the whole graph, we're just going to do enough of this work to find those places where the function can change sign. And then we will use multiplicities to figure everything else out, just like we did for the graph. But that's later. Right now, what I want to do is show you one more little thing to do with graphing rational functions. You remember that little star we placed next to our rule on vertical asymptotes? Vertical asymptotes come from factors of the bottom unless that factor cancels with the factor upstairs. So how do we deal with common factors of the top and bottom? I think the best way to explore this is with a silly example. So what we said before is that when a factor from the bottom is canceled by a factor from the top, that produces not a VA, not an x-intercept, but a hole in the graph. And I would like to convince you of this fact by looking at a kind of silly, simple example. So here is the silly, simple example. Let's sketch the rational function r of x equals x over x. And let's do it by plotting points. So here, there's only one thing going on upstairs and one thing going on downstairs. They're the same thing, so you could cancel them. But my goal here is to convince you that this will produce a hole. And the way I'm going to do that is by looking at a table of values. Now, the factor x is equal to 0 when x is equal to 0. So I want to keep my attention focused near 0. If I covered up the top and I just told you, here's a rational function, it has a factor of x downstairs, you would say, oh, that means there's a vertical asymptote at x equals 0, right? That's what that would mean. So let's see if we get a vertical asymptote at 0. In other words, does this function blow up as the x values get close to 0? So like -1/2 and 1/2, I would expect the outputs here to be very, very big, right? Getting big in here. What do we get? Well, if I plug -2 in, I get -2 over -2. And that's 1. If I plug -1 in, I get -1 over -1, which is also 1. If I plug -1/2 in, I get -1/2 divided by -1/2, which is also 1. In fact, I get 1 for all of these. This function, r of x, outputs 1 for any x value we plug in, except x equals 0, where r of x is undefined. Right, if I try to plug 0 in here, I get 0 over 0. 0 over 0 is not 1. 0 over 0 is undefined because the downstairs is 0. In particular, even for x values very close to 0, r of x is still going to output 1. So what does the graph of this thing look like? Well, let's plot the points. Call this -1, call this -2, call this +1, call this +2. So from my table, the point, call this 1. From my table, the point -2, 1 is on the graph. -1, 1 is on the graph. -1/2, 1 is on the graph. +1/2, 1 is on the graph. 1, 1 is on the graph. 2, 1 is on the graph. And even if I were to plug in like -1 over 1,000,000, something very, very close to 0, I would still get the number 1 as my output. So everywhere over here, this function looks like the line y equals 1. Everywhere over here, this function looks like the line y equals 1. The only place where this function is not exactly equal to 1 is at 0. And there we have a hole. Now, how could I have seen this faster? Well, r of x is x over x. And of course, you can cancel those. When you cancel those, the top and bottom both become 1. But when you cancel those factors, you are implicitly assuming that the factor is not equal to 0. So this is it. If you factor your rational function top and bottom and you discover that there's a factor you can cancel, go ahead and cancel it. But you need to make a note and say that your function is equal to that canceled version only for the x values that don't make that factor 0. In other words, for all x values except the x values that would make that factor equal to 0. And now from this, I can immediately see this graph. My function is equal to 1. It's a constant function everywhere except at 0. And at 0, it's undefined. And in particular, even for x values that are very close to 0, like right here, the function will still be outputting the number 1. Right here, the function will still be outputting the number 1. So there isn't some kind of asymptote or weird, like going to infinity behavior. No matter how close you get to 0, this function still looks like 1. It's just right there at 0 where it's undefined. And that means there must be a hole. Can't have any sort of weird asymptote behavior, because then, when you plug in numbers close to 0, you'd be getting big numbers out, right? You'd have an arrow going up or an arrow going down. If we look at what Desmos says about this guy, he looks like what we said. Right? Looks like the constant function 1. And no matter how close you get to plugging in 0, like over here, if I plug in negative 0.09, I'm still getting 1 out. Negative 0.08, still getting 1 out. Negative 0.08, can we get there? 0.04, still getting 1 out, still getting 1 out. And you can zoom way in if you want. Even with x equals negative 0.01, we're still getting 1 out. However, if you try to go exactly to 0, bloop, bloop, there it is. We're undefined. There is a little hole here. Now that hole should be infinitely small, should just be 1 point, and that's why it's so damn hard to click on here. But of course, when you draw these graphs, you can't draw an infinitely small thing. If you were able to draw it infinitely small, I wouldn't be able to see it. So we draw it a little bigger. But what's really going on here is that everywhere to the left of 0, this function is equal to 1. And everywhere to the right of 0, this function is equal to 1. The only place where this function does anything other than spit out the number 1 is right there at 0, where it's undefined. And that's precisely what this is communicating. So from negative infinity up to 0, but not including 0, this spits out 1. And from 0 to infinity, not including 0, this function spits out 1. But at 0, it's undefined. Because if you were to try and plug 0 into this original form, you have a 0 downstairs, which is not allowed. Any questions on this kind of silly example? Okay, let's look at a less silly example. Just a little less silly. How about something like x cubed minus 3x squared. Oh, no, I'm sorry, I'm so stupid. I was right the first time. That would be different. We could do that too, but that would be a little more complicated. X minus 3 over x squared minus 3x. Yeah, like that. I couldn't see. Good. Let's graph this guy. My first step, as always, factor top and bottom. So that top is x minus 3. That's just x minus 3 times 1. And the bottom, I can factor out an x, and I get x times x minus 3. And I can cancel the x minus 3s. So if you haven't yet, please take a look at the written comments on your exam 1. There are a lot of places where people tried to cancel things that we couldn't cancel. Remember, the only things you can cancel in a fraction top to bottom are common factors. So unless your previous step was factoring, can't cancel. So those x minus 3's cancel, and we learn that this thing is equal to 1 over x, but only if x minus 3 is not 0. So that means for all x besides 3. All right, we cannot say this function is equal to 1 over x at 3 because this function is supposed to be this function, which is undefined when x is equal to 3. And what this means is that there's going to be a hole at x equals 3, just like our last example. Now, everywhere else, it's the function 1 over x. So as I go to work on graphing this thing, I would run through that procedure with this simplified function. I do know what the graph of 1 over x looks like, and we could just draw that. That's one of our parent functions, but just for practice, let's go ahead and pretend like we're going to do all the other stuff. So do I have any vertical asymptotes? Yeah, x equals 0, and it's multiplicity 1. Horizontal asymptote, here the degree of the bottom is 1, right, x, and the degree of the top is 0, right? 1 is a degree 0 polynomial. So since the degree of the top is smaller than the degree of the bottom, our HA is the line y equals 0. So we've got our asymptotes. Intercepts, there are none. So the x-intercept we'd normally find by setting the top equal to 0. And again, remember, we're working with the simplified version. So that would mean 1 is equal to 0. But this is never true. So there are no x-intercepts. Y-intercepts, these come from plugging in x equals 0. But here, r of 0 would be 1 over 0 is undefined. We already know x equals 0 is a vertical asymptote. So there's no y-intercept. So I can start drawing my graph. Unlike that last problem, I don't have a base point to get started with. So last time I used my y-intercept as like a point that I could use to start figuring out the signs of the function in each of those regions. Here, because there is no y-intercept, I can't do that. So I should figure out one value of this function at least. Let me make a very small table, right? And this is as big a table as you should ever make when graphing a rational function. I'm going to plug in 2 numbers. When you plug -1 into 1 over x, you get 1 over -1, which is -1. When you plug +1 into 1 over x, you get 1 over 1, which is 1. So I can start by plotting 1, 1, and -1, -1. I also know there's going to be a hole at x equals 3, so let me go ahead and mark off where x equals 3 is. It's right here. Now, using this point as my kind of starting point, my base point, how am I going to approach this vertical asymptote? Will it be going down on the right or going up on the right?
Up.
Up. Got to be up, right? Because this point is positive. There are no x-intercepts in here. So I've got to go up here. Now, because this is an odd multiplicity vertical asymptote, will I be going up on the left or down on the left?
Down on the left.
Down, right? Because we have to change sign because it's an odd multiplicity thing. We also could have figured that out from this. Now, because this guy is negative and there are no x-intercepts over here, am I going to approach this horizontal asymptote from below like this, or from above like this?
Below.
From below. Good. And of course, you know what the graph of 1 over x looks like. We could have done this right away anyway. It looks like this. Now we stop as we get to 3 here, and we put in our little hole. Nice job done. All right, that's the graph of this function. I do have one question for you. Can you find for me the y value of this hole?
Wouldn't it be 0?
Undefined.
All good questions, all good statements. So when I say the y value of the hole, I mean like, why is the hole down here and not like up here or down here? It's true that the function is undefined at x equals 3. Yes, that's why there's a hole there. There is no point on the graph there. But the spot where I've punched out that point, what is the location where I've punched out that point?
1/3.
Oh, well, so its x coordinate is definitely 3, right? We know that. That's what we said earlier. The x coordinate there is 3. The y coordinate is the y value that would normally be on the graph there. So to find the y value of a hole, you plug the x value into the simplified version of the function. So here we get 1 over 3, right? I take the x value of the hole and I plug it into the simplified version. So this hole is at the point 3, 1/3. And you can use the hole as one of your points, right? So remember, I usually ask you to plot 3 points on a graph. So these would be my 3 points. Now this general procedure for finding the y value of the hole, this works all the time. So if you have a rational function with a hole, you discover that it has a hole when you see a factor top to bottom canceling, and you write down the x values for which this cancellation is valid. And then you say, okay, well, that means there's a hole at 3. That means there's a hole wherever this canceled factor would be 0. Then you run through your normal procedure to graph the function. Then it's nice to say exactly where that hole is. All right, it can help you draw the graph to say where that hole is. So in order to find the y value of the hole, you plug the x value of the hole into the simplified version of the function. This is something you're going to be doing in Calc 1 when you start to talk about limits. You'll factor and cancel some problematic piece and then plug into the simplified version. Okay, any questions about how I got this graph? All right, let's do one more. One more, and then I'll introduce the inequalities section. How about x cubed minus 2x squared over x minus 2? As always, I'm going to begin by factoring. Factor everything we can. So I can pull an x squared out from the top, and what's left is x minus 2. And the downstairs is just x minus 2, which is x minus 2 times 1. So I can cancel the factors of x minus 2. And what's left is just x squared over 1, or x squared. But this is valid only for x different from what? Where's the hole?
X equal to 2.
Very good. So this cancellation is valid for all x is different from 2. In other words, my function is equal to x squared everywhere except at 2, where it's undefined. So there's going to be a hole at x equals 2. And the y value of that hole is what? So we take this number and we plug it into the simplified version. So my hole is at the point 2, 4. All right, now x squared, this doesn't have any asymptotes or any weird bullshit, so we can just draw the graph. I know what x squared looks like. You know what x squared looks like. We all know what x squared looks like. It's this parabola we've been working with all semester long. The only thing is, it's got a hole at x equals 2. So there's your graph. And if you want some other explicit points, 0, 0, and say -1, 1. There we go, job done. Not bad at all, right? Okay. So that's everything I have for you guys on rational functions. There is one more little part in the textbook having to do with what are called slant asymptotes or oblique asymptotes. And while that is an interesting topic, it's not actually something you need for calculus. And so here at Santa Fe, we do not cover that portion of this section. And good news, at UF, they don't either. So if you're planning to transfer there, you don't need to stress about that. But it is something that's interesting. And if you find rational functions interesting, I encourage you to take a look in the textbook at examples 10 and 11, where they talk about this stuff, because it's fun. But you don't need it. We're not testing on it, so I'm not going to lecture on it. What you do need is the ability to solve polynomial and rational inequalities. So I'm going to go ahead and introduce that now to end up today. We have actually seen these before. At the very start of the semester, I gave you guys some problems from section 1.8, the review section, on nonlinear inequalities. These are special types of nonlinear inequalities. Since it's been a while, though, I just want to jog your memory, and so I'd like to do that by opening with a question. How might we solve the inequality 1 over x is less than 0? I don't want to put you on the spot too hard, so I'll tell you what, when I've seen people encounter this sort of thing in the past for the first time, a very common move is to say, okay, well, 1 over x is less than 0. Let me multiply on both sides by x. I want to try and get x alone. Let's get it out of that denominator. That would mean 1 is less than 0 times x. And then 0 times x is always 0. So that would mean 1 is less than 0. Okay.
So if 1 over x is less than 0, it means x is going to be less than 0. So it's going to be minus infinity to 0.
That's very good. That's correct. So you're a few steps ahead of me here. So this looks like kosher algebra, right? I multiply it on both sides by x. The x on the left canceled, just giving me a 1. And then on the right, 0 times x is 0. So what's wrong with this? Because 1 is less than 0. This is never true. Right? 1 is not smaller than 0. 1 is bigger than 0. So that seems to suggest that there is no solution. To the inequality 1 over x is less than 0. But from the graph, we all know what the graph of 1 over x looks like. From the graph, we see that there is definitely a solution. All right, here's the graph, y equals 1 over x. So 1 over x is less than 0 would be all of the x values where this graph is below the x-axis. And there are plenty of them right in here, right? So this part of the graph, 1 over x is less than 0 here. From, our solution would be all of these x values from negative infinity up to 0, just like you said. Let's say on negative infinity to 0. So why didn't we find this? Why didn't our algebra above find this solution? What's wrong with the black steps right underneath the question that we got 1 is less than 0, which definitely is not a true statement and has no solution, from 1 over x is less than 0, which by the graph definitely does have a solution.
We took 0, which is undefined, and that's why we cannot find it.
So the 0 here isn't so much the problem. The problem is multiplying both sides of the inequality by x is not kosher. So the answer to this question down here is that we can't multiply both sides of an inequality by x and expect the solution set to stay the same. Kind of one way I can explain this orange statement is that while it is okay to multiply on both sides of an inequality by a number, if that number is negative, the inequality flips over. Here, when I multiply both sides by x, I don't know whether x is positive or negative. And the resulting expression would depend on whether x is positive or negative. If x is positive, I would get this. And it's true that there are no solutions here that involve positive x values. But if x is negative, the inequality would flip over, and it would look like all the numbers x are solutions. So the kind of take-home lesson here is that we need to understand what kind of operations we can do with inequalities and what kind of operations we can't do with inequalities. It's taught to us very early on, at least in most schools, that you can treat inequalities like equations. You can add to both sides, subtract from both sides, multiply both sides by something, divide both sides by something. It's all good, the same way as equations. But the truth is that there are a lot of operations that you can do with equations that you cannot do with inequalities. I'd like to describe those legal operations to you now, and then give you a procedure for solving inequalities of this type. So. Operations we can do with inequalities. Turns out inequalities are actually way more important for calculus than equations. All of calculus is built around inequalities in a very, very real sense. And you'll see that if you ever take a class called advanced calculus or real analysis, everything comes from inequalities. So for example, you can square both sides of an equation, right? That's something that we do sometimes, but you cannot square both sides of an inequality. You can multiply through both sides of an equation by x, but we just saw that you cannot do that with an inequality. So what we can do, you can multiply or divide both sides by a constant. All right, we cannot multiply or divide both sides of an inequality by a variable quantity, but you can multiply or divide both sides by a constant. You just have to remember the inequality symbol flips. We say the sense of the inequality changes. The inequality flips if you multiply or divide by a negative number. The other thing we're allowed to do always, you can add or subtract any quantity. Constant or variable. On both sides. So we have to stick to operations that preserve order, right? Remember we talked about the real numbers being a complete ordered field? The only operations you can perform on an inequality without changing the solution set are those operations which preserve order. And many operations do not preserve order. Squaring both sides, taking square roots on both sides, reciprocating both sides, stuff like that does not preserve order. So these are the two things that we're always allowed to do to an inequality. The procedure then for solving a polynomial or rational inequality when we solve polynomial and especially rational equations, we're often tempted to do some stuff outside of this list. So we need to be very careful. Here's what you do. First, pull everything to one side. Pull all non-zero terms to one side, making the other side zero. Second, you may need to have a common denominator. Right? If you're looking at a rational inequality where there's like x's downstairs, you need to put everything together into a common denominator. Then combine all the like terms. your next step is to factor everything. Top and bottom. The places where the top and bottom are equal to 0, remember, those are x-intercepts and vertical asymptotes. Those are the places where rational functions can go from being positive to negative or negative to positive. So those are the cut points or the crucial numbers. You want to record. Your book calls them cut points, where the top or bottom are 0. Right, so basically you're finding vertical asymptotes and x-intercepts, although we don't call them that here. We don't need to. You can if you want to. Then you're going to plot those cut points on a number line. Which will divide the line into segments or into regions. And then finally, you will determine a sign in each region. So because your first step was to pull everything to one side, the inequality you're trying to solve is going to look like some rational function is greater than 0, or some rational function is less than or equal to 0, something like this.
Anya.
Now, once you've pulled everything to one side and rewritten your rational function as a single fraction, factored the top and bottom, the places where it can change from being greater than 0 to less than 0, or from being less than 0 to greater than 0, are exactly these cut points, the vertical asymptotes and the x-intercepts. So you plot those on a number line. That will divide your number line up into regions, and in each of those regions, your function will either be positive in that whole region or negative in that whole region. So once you know whether you're positive in one point of that region, you know you're positive everywhere in that region. And there are some tricks we can use here. I'm going to annotate this, just one other little thing here. Record or note the multiplicity for those cut points. Note the multiplicity of the factors of the top and bottom, because those multiplicities will be really useful for us. They will help us save a shitload of time. I want to look at an example. We have just a few minutes left, so I'm going to make it a quick example. So make sure you have these steps in your notes. So we're going to use them to solve the inequality x squared minus 4x plus 3 over x squared minus 4x minus 5 is greater than 0. So this is a rational inequality. I have a rational function and it is in an inequality. And thankfully, the first step has been done for us. Everything has been pulled to one side, right? All the non-zero terms are over here. The other side is 0. Everything's already been put into a common denominator, right? It's all just one fraction. And all the like terms are combined. I've got all the x squareds together, all the x's together, all the constants together, top and bottom. So steps 1 and 2 are done. Our next move is to factor everything. So that top, that's x minus 3 times x minus 1. And that bottom is x minus 5 times x plus 1. So my inequality is now this. All of these are multiplicity 1 factors. And my cut points, so this is like step 2, this is step 3. Our cut points, the places where this function can change sign, are -1, +1, +3, and +5, the places where those factors are 0. And they're all multiplicity 1. So now I'm going to take those and plot them on a number line. -1, +1, +3, +5. This chops my number line up into some regions. Here I have 1, 2, 3, 4, 5 regions. And I need to determine the sign in each region. Now, this is the tricky part. When we talked about this at the beginning of the semester, remember, I gave you problems like this at the beginning of the semester. When we did that, you were testing a point from each of these regions. Like you would plug in -2 here, and if this thing was positive at -2, you'd write a plus here. You'd plug in 0 here, and if this thing was negative, when you plugged in 0, you'd write a minus here, and so on. Now that we know about multiplicities and end behavior, we can do this way faster. The horizontal asymptote for my function x² minus 4x plus 3 over x² minus 4x minus 5 is the line y equals 1. All right, the degree of the top and the bottom are the same. So you take the ratio of lead coefficients, that's 1. What this means, it means that this function is approximately equal to 1 for large x values, right? R of x goes to 1 as x goes to either plus or minus infinity. So if I'm looking really, really, really far out here to the left, this function is very close to 1. In particular, it's positive. Now, because this is a multiplicity 1 feature, I will change sign as I jump over it. Right? That particular feature happens to be a vertical asymptote because it came from the x plus 1 factor downstairs. And that x plus 1 factor downstairs is an odd multiplicity factor. So my function will, if it goes up on the left, it must go down on the right, meaning if we're positive to the left, we're negative to the right. And I know I'm positive to the left because my horizontal asymptote was the line y equals 1. Next up, this feature at +1 comes from this multiplicity 1 factor, which means I'm going to change sign again as I jump over him. This time it's an x-intercept, but it doesn't matter. It's the same rule. X equals 3, that was also an x-intercept, and he came from this multiplicity 1 factor, so I change sign as I hop over him. And 5 came from this vertical asymptote, again, odd multiplicity, so I change sign as I jump over him. So the solution to the inequality is all the x values where this function is bigger than 0. Positive, right? Bigger than 0 and positive mean the same thing. So that's from -infinity to -1, unioned with +1 to +3, unioned with 5 to infinity. And that's your answer. And this is how we do it. So if you remember the multiplicity stuff, then this part is very easy. No more test points. Thank God, right? You remember doing this stuff at the beginning of the semester, so much time on test points. Don't have to do that anymore. All we need is the multiplicity of all of these factors and one extra bit of information to tell me the sign somewhere in here, any one of these. I used the horizontal asymptote to tell me the sign over here. Now, if this horizontal asymptote had been 0, 0 is neither positive nor negative, so I would have had to use something else. I could have used the y-intercept. The y-intercept for this function is +3 over -5, which means that when x is equal to 0, this function is negative. That would have given me this guy. And then I could have done the same thing that I did, where I say every time I hop over one of these, I'm going to change sign. So once you get the sign in any one of those regions, you can use the multiplicities to get the sign in all the other regions. Once you've got your number line filled out, you just write down the answer. It's really not bad. The only place this can get sticky is if this is a greater than or equal to, or a less than or equal to. And in those cases, you need to check the individual endpoints, just like you did at the beginning of the semester. So consider looking back through your notes from section 1.8 if this feels rusty. But then take a stab at the current homework. I did publish a new homework set for you guys just before class started. It has a little bit more graphing of rational functions, some of which have holes, and it has a few very simple inequalities like this. All of the inequalities that I gave you are like this one, where the first few steps are done for you. Now on Thursday, I'm going to walk you through some problems where those first few steps are not done for you, because I know that sort of algebra manipulation is something we need practice with. We need to practice putting together rational functions with a common denominator, and we need to practice combining like terms, multiplying out, factoring, all that shit. So please work on the current homework set between now and Thursday. That way, when you come in on Thursday, this part will not seem mysterious. You will have practiced it. And then on Thursday, I'll show you how to do some of that algebra. We'll get more practice with the actual manipulations. Again, this is something that's going to be on the test. Graphing rational functions, definitely going to be there. I am going to give you a rational function, say graph this thing, and you have to show me that full 5-step process. There will be rational inequalities on there, and it will not likely be one that is this easy. You will probably have to go through the whole procedure of getting to this stage by yourself. So take a look at this stuff. Please practice it. That way on Thursday, we can move at a decent pace through the remaining material in 3.7. After Thursday's class, I will publish one more homework and one more quiz, and then that will be it before exam 2. Exam 2 is going to be Tuesday. Yes. I'm sorry, was there a question there?
But are we going to have like a test review or not?
I'm not going to have like a day of class dedicated to test review, but if you want to work some review problems, office hours are great for that. I'm going to have 3 office hours between now and the test, tomorrow, Friday, and Monday. And I would be happy to spend time in that office hour working whatever problems you like. All right, if you cannot come to an office hour, send me a Canvas message or an email. We can try to arrange a meeting outside of that time. I might be able to find a little bit of time this weekend or something like that, but office hours would be preferred there. Any other questions before I let you guys go?
No, sir. Thank you so much for your help today.
Yeah, of course.
Thanks. Have a great
Thank
day.
you.
Yeah, no problem, guys. Take care. I'll see y'all on Thursday.